And we're back with Iskander. Hi, Iskander. Welcome back. Iskander already. It's not his first time at the GoWay stage, but first in the GoWay online stage. So yeah, we're happy to have you back. Let me say a few words about Iskander. Iskander is a senior software development engineer at VK.com in Russia, and in the past he worked on a Go compiler and third-party tooling for it, like static analyzers and utilities for refactoring. And now he plans to port many tools created for Go to the PHP ecosystem. Most of his interests are related to dev tools and programming languages. He's working on the Go JDK project that implements JDK in Go that runs quite fast and has nice Go Java interop. And now Iskander will be speaking about creating efficient VM with JIT in Go. So welcome, Iskander. The stage is yours.
Nice. Thank you for having me back on this stage. I want to say that I have a T-shirt with a GoWayFest logo. It's several gophers on some fancy backgrounds, but since it's hard to predict will it be seen from the camera or not, so I'm not wearing that T-shirt. And also another problem, I do not have a clicker, so I'm using something else. And this raises an interesting question, what other speakers were using when they were trying to switch a slide. Because if you're going to do it with a mouse or a touchpad, it's going to be a frustrating experience, in my opinion, because it's very different from giving a talk offline where your hands are usually free. So you can show something with your hands without trying to hold your finger on the button. So I'm going to start. And I will start with the backstory, so you know how I came there and why this is a thing. But the truth is, it's just because it was fun. So it wasn't something that is very practical. And if you're looking for a very pragmatic talk, it's probably not the thing, but it can be interesting and educational. Some time ago, we were speaking if we can use a Lucene search engine. It's not a search engine, it's more like a library to build a search engine. But nonetheless, we were trying to use it from Go. And, well, you can use that from Go, but it requires some efforts to do so, and I will explain why. Basically, you need to use a GNI, but you can't use that directly in Go. You probably need to use CGO. And you already know that there are some problems if you have these several layers of interrupt. So you have to use at least CGO plus GNI. And you can't pass arguments directly because you first need to pass your arguments to the method of Java class to CGO, which is not GNI. And then through the CGO, you pass that to Java and back. So even if you can handle some directions, it's almost impossible to return something from Java that can be mapped to the Go values directly. On the high level, you can see that this is a pipeline that will happen when you try to communicate with the JVM with this approach. And the slow part is trying to communicate with the GNI and Java through this layer when you're going to do a serialization and deserialization. Especially other thing that can be harmful for your application in Go, if it's a server or other thing that is multi-threaded or has multiple coroutines, is that you have to beam your coroutine to OS thread, because JVM or GNI handles for the JVM expect them to be pinned to the thread. If your coroutine switches the thread, there is going to be something like a fault in the application. So you have to use a runtime lock OS thread for every coroutine that is going to call into the JVM. That's not very convenient. You probably need a coroutine pool that were pinned. Also, you need to use a CGO for every GNI call. And by every, that means you need to create objects that are arguments to methods by the same thing. So if you want to call one method, it receives 3 objects, you need to call at least 3 constructors and 1 method. So that's a 4 CGO calls and probably some GNI machinery there only for 1 function call or method call. And the serialization between these processes, not the processes, but the runtimes can also be expensive. And Another view to this is, imagine that we have OS signals and your application, like Go, probably want to handle these signals. It makes JVM mad. It wants to handle these signals as well. We will discuss why they need to handle these signals, but right now it's just the picture that you can't make both of them happy. There is some approach that you can use to map both runtimes to these signals, but it requires some C code and dynamic library preloading. Right now we're using that approach, and we're using Lucene from Go application, but as you may have noticed, it's not very efficient, and it's interesting if we can do better. Can we use a Java application or library from Go without paying all these costs? And if you're interested in how expensive that is, on my machine, or you may notice in Matt's talk, he told that a function call is approximately 3 nanoseconds. That's almost correct, but it also depends on the cache. So the first call is going to be much more expensive, but if you run a benchmark, at some point it will be very cheap. But if we take this as an example, like 3 nanoseconds, one call of the GNI or Java method can call 10,000s of nanoseconds for one call. It depends on how you implement that, but it's hard to make it faster without ruining the concurrent application. So we are finished with the backstory, and let's discuss how my hobby project is going to address at least some of them, and how can you implement that in your own hobby project or in something that is production ready. Let's try to build an efficient Java virtual machine that can be embedded into Go application. That's a quote by me. I just said it. What exactly do we want in that library or runtime for the Java? We want it to make possible to call Java from Go quite cheaply without CGO. We also want to run optimized machine code without trying to interpret that, because interpretation is going to make your code run 10 times slower, at least. And we want efficient object layout and allocation. We probably want to use Go runtime, like memory allocator and garbage collector, so we don't have to re-implement them. But there are some problems, Go-specific problems, that we're going to solve as well. Let's do it. If we're going to directly connect our JDK, the JDK is like compiler, runtime, the tools that are going to be used by a developer to build an application. If we're going to connect them directly, it can be quite fast if they're using the same model of the object and if they don't need different runtimes to be present at the same time. And the Go JDK project from the high-level architecture is a set of libraries and some tools. Like it has a Java tool that can print the bytecode in intermediate representation. It also has JIT compiler that is not tracing. We will discuss that later. You can follow the link. It has basic implementation and examples as well as tests. We're not going to cover the Java translation from the source code. We're going to take class files that you can generate from any Java compiler. You take a Java source file, you compile it to Java class, and this is where we start. So we're using the class files as an input. Then we take that class file that we're going to decode and transform it into something that we can use. There are several steps. We will discuss some of them. And why the JIT compiler is not tracing? Because every time we're loading the dependencies and the classes, we're generating the code right away. And then we get the loaded class data and some constants. It depends on the class file. If it contains static data, we get some handle that can be used to call methods and get the runtime information like type info for the classes. How can we make the code run fast? You have a bytecode, metadata constants in your Java class file. What we're going to create out of that to run fast? As I already said, we're going to use a machine code. We're not going to try to interpret that. That's a different topic. I don't have time to explain it right now. As you will see, we already have limited time for this subject. So let's start by converting the bytecode into the machine code, the direct translation from the bytecode. We will take this class as an example. It has only one method, adds1, and it returns the x increased by 1. This is the first implementation I actually did. I think it's in the Git history on the Go JDK project. On the left, you see the bytecode instructions. On the right, you see the AMD64 machine code for that was generated for that. I highlighted the stack bookkeeping, so it increases and decreases the stack pointer. On the left, you can see that those instructions are not really easy to understand or analyze and optimize. So we're not going to use the stack architecture that don't have arguments. If you look there, there are no explicit arguments. It's on the stack. So if you're interested into the stack versus register virtual machine architecture, there is a great topic there, the paper on that. It also covers how you can convert the stack code into the register-based virtual machine, basically. So instead of generating the machine code from the bytecode, we're going to create an intermediate representation that is register-based, but I will call registers as slots because register has some different meaning in the hardware. And we're going to create the machine code from that. From the bytecode, we can create the intermediate representation that is presented on the right. It looks almost like the LLVM IR. It has destination of the instruction on the left of the equal signs, and then it has instruction with arguments. So as you see on the left, the arguments are implicit. On the right, they're explicit. This is far easier to analyze. If you generate the machine code, as you see, there are less instruction there, so we do less work. And this can be even further optimized. As you see, this is a dead store. We are storing into local just to move it back to the register. If we make our intermediate representation even smarter, like we have special destination like return, we can generate code without optimizations. And when we know that we're moving to the return value, we just move it to AX register or anything that you map for the return. And then we make a simple return without moving. Now we're going into the Go specific details. Before that, it was only like simple theory, what we're going to do. We need to understand the function frames before everything else to understand what slots is. When you call a function, a new frame is created. It can have a different size, and it's like a stack. So it always grows, and then it goes back, so it shrinks when you return. This concept is interesting because we will implement something like a lazy garbage collection with that. And every function frame, as you've seen there, consists of different slots. They are categorized by different classes, like arguments, locals, and temporaries, but they all have the same structure. And the structure is like a slot objects. We will discuss what this is later. As you see, we call them R, like a register, and they can have different classes, like arguments, local, etc. What is a slot? A slot is basically a storage unit for your execution environment, like a virtual machine. It can store scalars and pointers. And if you think about it, it seems like everything can fit into 64 bits because pointer on the 60-bit machines are 8 bytes as well as long. But integer can occupy half of that slot. That's not a problem. There is a slight problem here anyway. If you look at here, if we use unsigned int 64, we can store a pointer there because the Go garbage collector is not conservative. If it's not a pointer type, it's not going to hold the value of the data being pointed. So you can't store a pointer there. It's going to be garbage collected. If you try uint pointer, that's actually the same. It's not. It's like a weak pointer. It doesn't hold the data. If you use unsafe pointer, you have opposite problem because you can't store scalars there. When the garbage collector receives the unsafe pointer, it will try to deallocate the memory. And there is a check in runtime that says that, hey, this is not the memory that was allocated. You have some garbage there. That's a problem. So you can fix this by having a slot of 2 fields. One holds only scalar data and other field holds only pointer data. You double the size of your frames, but you avoid the problems. I haven't found a solution that doesn't introduce other problems, but I heard that Go team does consider to have a conservative garbage collector. If they ever have, you can store your pointers into just uint64, and we don't need 2 fields. But others, before I discuss other solution, so as you see, how do we garbage collect anything? We don't allocate it ourselves. We can't garbage collect it ourselves as well because the allocator is a different thing. Garbage collector is implemented with Go, not by us. Well, on the frame, you have these pointer fields. If you want to do a garbage collector, you just go through the all pointer fields and set them to nil. If Go code that uses your GVM doesn't store any pointers, those values become unreferenced, so they will be garbage collected, and you can reclaim your memory like this. Other solution can include having two stack frames or function frames. One of them reflects the scalar values only for pointers, so we can keep them alive, and so the garbage collector sees them. But then you have to maintain two frame pointers. And let's talk about more interesting thing. And if you think about how you call the just-in-time compilated code from Go, that's simple. You just memory map by a syscall memory, mark it as executable, then you store a machine code there. And either you can cast it with unsafe to a function, or you can pass that code pointer into the assembly and do a jump into that code. It will work. There is no problems there. But if you're going to call a Go from Java, if you want to have a nice interrupt in both directions, that can take some efforts. For example, you need to know the Go function address. So when you generate the Java code that goes to the Go, it needs to know Go function address. That's not hard. You need to follow Go function calling convention, and it's harder because it's not very well documented and it might change over time, although it was the same for several years now. And the hardest part is you have to deal with fatal error issues. Go doesn't support just-in-time compiled code at all. Getting a function address is simple. You only need to have some helper function that can translate the Go function value. It's easier to do this by the empty interface because we know how it's represented in memory. It always stores its value by a pointer inside it. So if you dereference the pointer and you take a pointer of that pointer, basically of the function value, you get the function code. I hope I explained this in a simple way, but that's not very interesting anyway. Go calling convention is well explained in the presentation of Michael Monday from the IBM. The source is in the link. This is a slide. There is no point in discussing this right now, but you need to understand how it works. And the calling convention makes it like this. You push all arguments to the stack, then you call a function, and after your function returns, you move the results from the stack to local slots. This is how you're calling Go function. Well, let's try it. Go Runtime is not impressed. It will crash your application with some of the issues you see here. It's probably going to crash. You can't really even return to your code. What happens there is that you're calling a Go function foo from unknown position. So when you generate a JIT code, it has some unknown to Go compiler address. You generate that code after the compilation starts, and Go Runtime wants to have a stack map that is known, that is embedded into the binary. As Lance Taylor said, if you're going to call a Go function from an assembler, it's a problem, right? That's not something you want to do. And basically, he's right, but we're writing a JIT compiler. We need to do that. So let's try to do that. We have some powers to show. We can fix this problem by introducing a proxy. You can also know this technique by a trampoline name, and this fixes both problems, or all problems that can arise. The picture with a trampoline will look like this. We're calling a call Java function that is known to the Go compiler during the compile time, and we call the Go code from that known place in the Go binary. So we do a jump from the JIT'ed code into that place, call the full function from there, and then we want to return to the JIT code. We return from the call Java wrapper, like a proxy or trampoline. This might look a little complicated, but it's not really is. What we do is we're trying to fix a stack map pointer. You can Google about this, but you basically can add here this macro. I'll explain why it's safe. It's safe because if you don't rely on the Go stack value addresses, why? Because Go stack can be resized and addresses will be changed. If you don't have anything that takes address from the stack, you're safe. And as well as your heap values are reachable elsewhere. This is the case for us because all values that are going to assembly function are escaping, at least right now. And this is our trampoline target, where we call the Go function from. So we jump to a Go code from the JIT code, and this fixes the unknown PC address for us, because the program counter is known from this location. And the GMP at the BP is the return address that we write when we call the Go function from the JIT code. We need to extend this a little bit, so we need to store where we can return from that call. This might be a little complicated right now, so please prepare yourself. I explained this in the 3 steps, but basically what it does, it's one instruction that moves a relative instruction pointer address to the location after the jump. But because Go doesn't have convenient relation instruction pointer addressing mode in assembler, I had to encode this using the byte sequence. And jump to a function register is executing the just-in-time compiled code. Let's try to beans our native function and methods in Java in GoJDK. In Java file, you're going to have a native function method. In Go, you're going to have a simple function. And then before loading a class, you bind that class method to some Go function. That will work, and we will get quite fast function calls. I think it will be around 15 or 10 nanoseconds, so it's quite fast to call a Java method from Go, and it's about 15 or 20 nanoseconds for calling a Go from Java, so it's quite fast. And it can be optimized probably even further. Let's talk about the object layout and memory allocation. If you want to allocate this class, you're probably going to think about something like this. It's perfect, but it's impossible. It's impossible because you can't express every class statically while you're compiling your code because you don't know which classes you're going to load. So many people try to use interfaces or reflect field to express arbitrary set of fields. So your object going to look like a slice of arbitrary object interfaces. And the first field is this element at the index 0, etc. And you're going to store an address of that value because we store pointers, not interfaces in our slots. If we look at how we're going to access the field, it's going to be messy because we have to dereference a slot pointer when we get element of a slice, when we need to dereference empty slice element value, and this is to only get one value. That is the way to get a class object member field. What we can do to more effectively map objects is we can have a common object header. So everything that goes there is shared between all objects. This pointer data is a pointer to pointer because we want to store several objects there. All pointer data goes there, so it's visible to a garbage collector, as we will see. And this is sized object. We'll discuss what sized object is. This is something that can store scalar data that is flat and it can be accessed fast. This data is going to be used to store 2 fields. Every one of them stores occupies 4 bytes, so we can use 8 bytes to store X and Y fields. And we can convert between the two relatively safe. It's always safe to convert the object to sized object because that's the rule of the unsafe, casting from the smaller to bigger. But it's not safe by the definition of the unsafe package to do the opposite direction. But runtime does this. The Go runtime does this. So it's actually okay, but you're going to lose at some point if they change that. So you have to be really careful. If we try to look at this at the different direction, this is how it will look in general. Abstract model is like you have pointer data that references to a slice, but not really a slice because we don't want to store length and capacity. That's just an overhead because we know the size of the object precisely. And these are reachable for the garbage collector. These are not reachable for garbage collector. And that doesn't matter for us. We're only using the header so the garbage collector sees what it needs to see. For the foo objects, as we said, the X and Y will be located in the scalar data, and the bar field will going to be allocated in the pointer data. And when we look at how we access a field here, it's just one dereference at the appropriate offset because our object, as you've seen, is flat. The non-pointer data is at the same object as the other fields. For pointer data is slightly more complicated because we move by the indirection all these fields, but that is required so the garbage collector can work. And how do we actually allocate these? You can't use the make byte slice, because when you allocate, Go garbage collector will memorize what, not the garbage collector, the memory will be marked as something that doesn't contain pointers. So even if you allocate byte slice, then you cast it to something that contains pointer. Unfortunately, Go runtime or garbage collector will still collect this data, because when you allocated that, it was said not having any pointers. So this is why we have different sized objects, and we separate them, this sized and unsized. We can allocate the closest object size. That means that if we need 8 bytes, we are going to choose object 64. Then you allocate that object and return it as a general object header. If you didn't understand the concept of sized object, here is an overview. So you will have a lot of static definitions of this. This looks like a Go allocator size classes. So you have some size classes, and when you allocate something, you try to choose the closest fit and to avoid memory wasting. So let me speak about the limitation and challenges that you can find while implementing this. The null pointer check is one of them. If you insert explicit null checks, it's going to be quite slow because you have to make these checks every time. In hardware, it can be actually more efficient. Like you can use the hardware exceptions and interrupts in combination with OS signals handling. It's just going to be faster. There is a link that explains that. But as you remember something like this diagram, our runtime can't really use these signals because Go runtime uses them on its own. So we can't use this approach. This is a problem that needs to be solved. Other limitation is that, remember, we are going to convert the bytecode into the machine code, but for some reason, Java programmers like to manipulate the bytecode. When they're loading their application, they can dynamically change that code. And we don't have that bytecode. You can't manipulate on something that doesn't exist. This can be solved, but this is a problematic. Another challenge is hot reload of the code or method reload. If we're going to do inlining, or if we're going to do other optimizations and we eagerly convert every code and we don't have the original code, it will be hard to know which places you need to update after that. So you need to have data structures that map all code that were a subject of inlining optimization. So you can update the code that was inlined. That's not very simple, but it can be done. In the closing word, I want to say how you can test that. The easiest approach is to have one set of files instead of several sources for this. And every test is going to run some programs and then print them. For this case, you need some wrapper around the standard library. In the OpenJDK, it's going to be system.out.println. And in GoJDK, it can be anything like fmt.println. We could use the system.out.println, but then you're starting to implement the JDK. You're probably not going to have a classes support with some fancy output methods. And if you wonder how well it behaved, for the just-in-time compiled versions, we had not that high difference in execution time for the end-body benchmark. I think for the new implementation, that's quite well. I didn't use any optimization in the code. So machine code that was generated is very naive. So it doesn't have the copy elimination or something like this. If you look at the version without the just-in-time compiler, if you're going to implement the interpreter of the Java virtual machine in Go, it's going to be twice as slow as the OpenJDK without just-in-time compiler. You can turn off the just-in-time compiler by a flag. So I try to match these numbers, so it's a fair comparison, but twice as slow is not a good result for the virtual machine. At least I think so. These are very useful resources. These are not all the links that you can use, but I think these are the most useful ones. Thank you. I hope I made it in time. Now I need to write to Daria. I see that I have 10 more minutes. It was hard to me to tell if I'm going too fast or too slow because I didn't have a timer The reason is because I'm not using the Pine tool to present, because it doesn't have any hotkey to switch a slide. So you have to press a touchpad or mouse. So I used another application, external screen sharing, so I didn't see a timer.
It was hard to meet.
Hi. So thank you for your talk. And yeah, I can see one question in the Q&A tab. Is the solution compatible with the debugger? I don't expect to debug Java code, but at least see some sane stack frames. Question from Christian.
The only way I was able to debug that code is using the GDB. It was basically just debugging the machine code. There is no any ways of mapping the source code right now. And it wasn't the point of my project. I wanted to try to do something that was considered impossible. If you look at the Go issue tracker, there are at least 2 issues that were closed. The people asked, how can we call the dynamically generated machine code from Go? The answer was, you can't. Go doesn't support that. It will crash. But you can do this if you're using this trampoline trick. There are probably other tricks.
Okay, and yeah, while you were replying, Christian wrote another one. Was the original goal of making runtime efficient achieved? The longer compilation time is only lost as at startup, but what about the actual execution?
The execution is almost as fast as OpenJDK version, because if you can generate the efficient machine code, there is no reason why the alternative implementation is going to be run slower. If you write the runtime in Go, as was originally intended, there can be a difference between C and Go, but the code for the Java itself that was compiled to machine code, it only depends on the quality of your compiler and optimizers. The interesting idea is that you can take your Java class, optimize the bytecode, and after that, feed it to your just-in-time compiler, so it's easier for that to optimize code further.
Okay, thanks a lot. Thanks, Christian, for the questions. So if anyone else has any questions, feel free to drop them here in the chat while we're here. Oh, there is anyone. Amazing, mind-blowing stuff. Thank you. It's not exactly a question, but thank you for the comment. Let's have a look in the public chat. Maybe there is something. No, only thanks for the talk.
I would also suggest to go to the Golang Nuts, the mailing list. There is a Jan Lance-Taylor that usually answers the hard questions. So when I try to ask him, not him directly, but on the forum, usually it's him who answers this question, like, what will happen if you call a Go function and everything crashes? Jan Lance-Taylor usually knows the answer.
But there is one more question. Do you see any potential use cases for this amazing approach?
Honestly, or I mean, in order to make it production ready, it requires so much work, at least several years. Otherwise, it won't work in all cases. And that's not very interesting, because you have some interesting parts in that project, but after you do that, other things are more routine. You need to implement everything else, basically. And not every feature has its challenges. Some of them just require you to cover a lot of cases. And Java Virtual Machine has some interesting features. Not every feature is required. It also has a big standard library. You probably want to implement that as well, or map it somehow. So it would be practical or promising if someone would do that, because you would, as I said, we were trying to use a Lucene from Go, so we can implement the searching engine in Go application by using the Java library. If we could do this efficiently, that would be great. But since we're okay with the performance right now, I'm not sure that someone is going to pay for that. And if no one is paying for that, it will never happen. There are some people who can work on the same project for several years, but I'm not one of these people. At some point, it becomes boring.
That's true. Okay, and we have one more question from Daniel. He's saying, sorry, he joined late. I hope it wasn't part of the talk. Did you compare memory consumption in addition to execution speed?
That's an interesting question, but it depends on how to compare. I need to add the benchmarks, I think, and measurements for some application. The problem is that there are not that many programs that you can run with that. I haven't implemented all features, like it can't execute any arbitrary constructor right now. I only figured the allocations idea, and I tried them on the arrays, and it works. Probably it's going to be relatively as close to Go as possible. The only overhead you have is indirection for the pointer fields and the metadata. Everything else is just Go objects. How it compares to the Java internal implementation of OpenGTK, that's a question that can be answered only if we support something that can compile more complicated programs. I can say for simple objects, but that's not very interesting, right?
Okay, and we get more questions. So the next one is crazy idea from Christian. Could this trampoline be reused for the still half-implemented plugin supporting Go?
I actually was disappointed by the plugins that much, so I never really tried to come back to them. Almost every time when we tried to use plugins, it wasn't a good experience, especially that you can't unload them. And the compilation time of the plugins were so slow at the beginning. I heard that right now you can compile a plugin faster because Go compiler now uses better caches. But in the beginning, it was like 1 minute or 30 seconds for one plugin. It was too much. So you can't implement system like Emacs that compiles the code on the fly and then loads that. I'm not sure about if you can use the trampoline trick with the plugins. The problem it solves, it calls the code from the different context that is known to the runtime. And if you're, by the way, there is a interesting point to the Go asynchronous preemption in the newer version. Your assembly function is not going to be preempted if it contains no pointer macro. So you don't have to worry about that. But it also means that while your just-in-time code runs, that Go routine can't be asynchronously preempted. But it can be preempted if you call a Go function from the just-in-time compiled code. I think I could have talked slower. I tried to be fast.
No, well, we're right on time, actually. So if you folks have any more questions, you can ask them to Iskander in his speakers room, in the speakers page. And after that, we'll have a short break. And after which there will be a panel discussion with the speakers from last year's edition. So I hope you will all enjoy it. And yeah, there is still sponsored booths that are open, and you can go and check out what's prepared for you there. So once again, thank you, Iskander, very much for your very informative talk. It was great. And yeah, you saw that many people liked it really a lot. And yeah, we'll stay in touch and see you soon in the speakers room.
Bye.
Thanks a lot. Bye-bye.
And now we have 10 seconds to wave.
Woohoo! Smiling and waving.
Yeah, and smiling.